talking about depletion and how it affects the different geomechanical effects of reservoir depletion. And last time we talked about specifically inducing faulting due to depletion. Today we'll talk a little bit about another thing that can happen, that is stress rotations. So it's been observed that the far field stresses seem to reorient near to the localized sort of axes of a fault. So if you imagine there's a sealing fault traveling through a reservoir, if the original far field stresses are oriented as they are here, so this would be the direction of SH max. After some depletion, some local observations with tilt meters and other things seem to indicate that the stress reorients locally. You know, when I say locally, I mean near the fracture, right? The stress tends to reorient near the fracture after some depletion to align with the fault plane. And so if we have a little representational cube with some far field stresses applied to it, like so. Of course, it's in equilibrium, right? And if there's a sealing fault traveling through the middle of it, and say we have a well over here, and we're going to deplete that well along some stress path. So if you remember, we defined last time, the stress path is like the change in horizontal stress with respect to pore pressure. So, and remember, there's some a lot of assumptions here. The isotropic, homogeneous and isotropic permeabilities equal horizontal stresses and whatnot that define the stress path. But if this fault lies at some angle theta to the far field stresses, then just using the geometry, we can resolve the stresses on that fault. We could do it with you know, our rotation matrices like we did earlier in the class, but here it's not necessary because we're sort of looking at just a planar view of a lateral fault, and so you can just use simple geometry where if this is a normal vector on the fault and there's some traction associated with that normal vector Tn, then you can actually just write the components of that directly just using geometry of the fault, where if you have some local coordinate frame xy that's aligned with the principal stresses, then the stress in the x direction is equal to SH max times minus A delta P, right? So this is the perturbation due to depletion, right? So after if we're going to deplete at a rate A, right, then the perturbation of the stress on the fault is going to be equal to what the original stress is minus the perturbation. And because there's some associated, you know, we're assuming the fault is in equilibrium. So there's a normal stress on both sides of the fault and a resulting shear stress on either side of the fault that's holding it in equilibrium. In this case, again, we're considering like a sealed fault. And because that's going to also deplete at the same rate on either side, the change of stress is going to be equal on both sides of the fault just due to equilibrium. So in other words, the fault is sealed, so there's no fluid change across it, but because it's in equilibrium, any stress change on this side is also going to occur on that side. Has to, right? Otherwise, the fault would slip. So then that's going to be A delta P over 2 times 1 minus cosine 2 theta. So again, we're assuming that because it's homogeneous and isotropic, the stress is depleting. SH min and SH max are depleting at the same rate. and then there's a shear stress like that. And we didn't talk about plane strain model, but plane strain is an assumption when you have a three-dimensional stress state. If you have one dimension that's laterally that's extensive, right? Sometimes we use a plane strain assumption where we're basically saying in that thick direction, in the thickness direction, the strain is approximately 0. And when we make that assumption, you can reduce the Mohr circles to a two-dimensional Mohr circle. So in 3 dimensions, you have 3 Mohr circles, right? But you can make a reduction to a 2D plane strain Mohr circles, and in doing that, then you can evaluate how the stress would change through some rotation angle. And here we'll call the rotation angle gamma. And from that, so this is again from plane strain Mohr circles, then you get this guy. And so if you plug in those 3 values into this equation and make a bunch of simplifications, and that's really what we're interested in, and not why I didn't go into all the details of the Mohr circles thing, then you get an equation like this, where A is defined as we've defined it before, and this Q is just this parameter, right? So you can get some local reorientation due to depletion, and I think, did I leave out the, yeah. I think I left out the case study in this case, but if you want more information, you can look at this in Zobac's book, where they made some qualitative comparisons to this very simplified model to some case studies in some fields. I think what's more interesting with respect to stress changes due to depletion nowadays is related to hydraulic fracturing. So in fields where you have sort of a low stress difference, like in the Eagle Ford Shale, for example, you have a fairly low principal stress difference to begin with, then depletion over a fairly short period of time can actually cause a stress reversal. So in other words, this rotation will actually reverse the direction of the principal stresses. And what that means for completions design is that, and we're going to talk more about hydraulic fracturing in the upcoming weeks, and kind of last few weeks of the semester, but if you remember, hydraulic fractures, you know, in theory anyway, always grow perpendicular to SH min. So if you have a stress reversal, meaning SH min and SH max change places, then you can actually go in and refracture the same well. You don't have to drill again, right? You can go in and you can refracture the same well, and you can access new parts of the reservoir with those fractures. And so that's an interesting feature, especially or an interesting thing to investigate and understand, especially in sort of low price times, because half the cost is drilling it, right? Well, if you don't have to drill the well, you can just go in and recomplete it and get a significant amount of additional production, then it can be cost effective to do that. So when you hear about refracturing, that's kind of the idea there, is that you've depleted the well for some time and you anticipate some change in the principal stresses, either a complete reversal or a significant rotation, and then you can go in and refracture it. So we'll also then talk about